On this lesson, we're going to be discussing the trigonometric form of complex numbers. Let's get started. So let's start by looking at this introduction question, which states the following plane is called the complex plane. So right here, notice that it looks like a regular Cartesian plane with the x and the y-axis, but notice the difference as to how we're labeling our axis. Remember that for any complex number, it's always in the form of a plus bi, where a represents the real part and bi represents the imaginary part. So instead of labeling it x and y axis, on my x axis, that's going to be representing the real axis, or at least the numbers that correspond to the real part. And instead of calling it the y axis, we're going to call that the imaginary axis, or at least the axis that are going to be representing the imaginary part of the complex number. So this is what we call the complex plane. Instead of an x-axis, we call it the real axis. Instead of a y-axis, we call it the imaginary axis. Now, let's plot a point that is 3 positive units in the real axis and 2 positive units in the imaginary axis. So in that case, 3 units that are positive in the real axis, so that's 1, 2, 3 units on the positive axis, and 2 units positive in the imaginary, so 3 on the real positive and 2 on the imaginary positive. So we have it right here. Now, you can see it at this point as just being 3 units on the real, 2 units on the imaginary, which you can see it as just being as 3 comma 2. And I'm going to put quotation marks. You will see why in a second. Now, let's find the distance from that point to the origin. So let's try to find this distance. Let's try to find the distance from this point to the origin, or the point 0, 0. Let's try to find that distance. For recall that the distance formula is defined as x1 minus x2 square plus y1 minus y2 square. And at least my x1 and y1, I'm going to make it the origin, and my x2, y2, I'm going to make it the point. So let's find that distance. So we're going to have x minus 3 square plus 0 minus 2 square. That's just negative 3 to the second plus negative 2 to the second. So now that will be 9 and 4. So now the distance is the square root of 13. So how can we tie all this together? Well, this point can be seen as the representation of a complex number. Because notice at this point right here, so the point in our plane, the point in the plane, this point right here, it's the representation of the complex number z. It's a complex number who is 3 units that are positive and 2 units that are positive. So notice that this point can be seen as also the representation of this complex number. And now, if we were to take the absolute value of that number, the absolute value of 3 plus 2i, but the absolute value of a complex number is nothing more than the distance from that point to the origin, which we already found it right here, which is just the square root of 13. So this is how we're going to be combining everything together now. Now, what we have just shown here is that we can represent complex numbers now in the coordinate plane, where the first portion of it represents the real part, which if you have a positive number, you will represent it on the right-hand side. If you would have a negative number, you would represent it on the left-hand side. The complex number is represented by the y-axis. If the imaginary number is positive, then we'll represent it on the upper. If the imaginary is negative, then we'll represent it on the lower. And if we put it all together, we can actually find a location. And we're going to be taking a look at examples where we want to take the absolute value of such imaginary numbers. But just recall that the absolute value of an imaginary number is just the distance from the point in the plane all the way to the origin. And again, just to recap, any complex number, which again, for complex numbers, we're going to be using the letter z. Any complex number can be defined as just a plus bi, where a represents the real and b represents the imaginary. So here, let's just summarize what we have just done. It says the absolute value of a complex number, and notice that here is how we define a complex number, is nothing more than the distance between the origin and the point, which is defined by the complex number. And the absolute value of a complex number, it's also given as just the distance from the origin to that point, which the origin, it's always going to be 0, 0. So therefore, the distance can just be seen as just the real square plus the imaginary square, because that's exactly what we just did here. The real square plus the imaginary square. Now let's just practice this a little bit more. Let's use the points in the complex plane to perform the following. Let's write down the points in the complex form, and let's find the absolute value of the complex number. So I'm just going to be doing 1 or 2, because the third one might just get a little bit repetitive. But let's just take a look at my first coordinate point right here. Let's take a look at z, z1. So let's write down the point in complex form. Well, notice that this point has 2 units on the positive real axis and 2 units on the positive y-axis. So therefore, this number, z1, can be defined as 2 on the real and 2 on the imaginary. So this complex number can be defined as having this location. Can we find the absolute value of this complex number that we have just found? Yeah, well, the absolute value of z1 is just going to be the real square plus the imaginary square, which in this case is just going to be 2 squared, that's 4, so that's 4. So z1, the absolute value of z1 is just the square root of 16. I'm sorry, I was thinking multiplication, but obviously 4 plus 4 is not 16. 4 plus 4 is 8, so they just change that. So that is 8. And this can be seen as just z1 as being 2 square roots of 2. So notice that this is a pretty good analysis of this coordinate point. We know its location, 2 in the real, 2 in the imaginary, and I know that the distance from this point to the origin is just 2 square roots of 2. So let's just try one more point so you can get the hang out of this. Let's take a look at z2. So first of all, let's start looking at where is the location of z2. Well, notice that z2 is negative 3 units on the real axis and positive 1 unit on the imaginary axis. So therefore, my complex representation of this location will be negative 3 plus 1i. This is saying that the real is negative 3 and the imaginary is positive 1. So let's just find the absolute value of this complex form. So the absolute value would just be the real square plus the imaginary square. So now this just becomes 9 plus 1. And again, we're adding, we're not multiplying, just like I thought about it before here. So this is the square root of 10. And let's just keep it as this. And z3, I'm just going to leave it for you guys to think about it. But I feel like after the examples, you might get the hang of it. So let's actually go a little bit deeper into this. Because now, thanks to this, we can start thinking of ways to represent complex numbers using trig functions. So remember that a complex number can be written as a plus bi. Now the question is it possible to write down a complex number using trig functions? Well, let's see. Here, imagine that we want to represent this point right here, a comma b, using complex numbers. So here we have a complex numbers whose real it's of negative a, and whose imaginary it's of positive b. So how can we think about this? So is it possible for me to represent this number using trigonometric functions? Well, the first thing that you might notice is this. We can create a right triangle. And we can think of theta 2 as being my reference angle. So I'm just going to concentrate on this right triangle right here. I'm just going to concentrate on this right triangle right here. So what do we know about this right triangle? Well, if this is my right triangle, and this is the reference angle, theta 2 is my reference angle, then definitely B will represent my opposite. A will represent my adjacent, and R represents the hypotenuse. And notice that since we can represent this using the right triangle, then we can use what we know about SOHCAHTOA. We can think of SOHCAHTOA now. Because let's see what happens if we try to represent this using SOHCAHTOA. Let's find the sine of this angle. Let's try to find the sine of this angle. Well, the sine of theta 2, that will be opposite over hypotenuse. But notice that my opposite is going to be b, and notice that my hypotenuse is r. And if I multiply r to both sides, r will cancel out, and now I know that the b component is equivalent to r sine of this reference angle. So now notice that this portion that we do have here, the y component of this location, it can be represented just r times the sine of theta 2. And I want to be clear that we're using this little reference angle and we're not using theta. So we're using theta 2 because this is the angle that we use to define this triangle. We're not using this angle to define this triangle. We're using theta 2. So therefore, we must take the sine of theta 2. So now notice that we know that the b component can be seen as just r times the sine of theta 2. So what would happen if we find the cosine of this reference angle? Well, recall that cosine is adjacent over hypotenuse, and adjacent is a, and hypotenuse is r. And if we multiply r to both sides, notice what we're going to end up with. Now we're going to see that the a component is equivalent to r times the cosine of theta 2. Now, if we put it all together, remember that a complex number can be seen as a plus bi. But I know that a can be seen as r cosine of my reference angle, and I know that b can be seen as r sine of my complex angle. So if we put it all together, now we can see that any complex number, which is z, can be defined as just r cosine of my reference angle plus r sine of my reference angle. So this is one way that we can represent complex numbers as r cosine plus r sine I. Forgot the I there. But we can still simplify this because notice that they both have an r in common. So now we can represent it as just r times the cosine plus I sine. And this is something very important for you to recall because any complex number can be defined as a combination of r's and cosine, where cosine of theta will give you, or r cosine of theta will give you the real part, and r sine of theta will give you the imaginary part. So this is how we can represent complex numbers using trigonometric functions. But there's still something that we still haven't discussed. So I know that if I take the sine, I can use it to define the b component. And if I take the cosine, I can use that to define the a component. But out of curiosity, what would have happened if we would have taken the tangent of this angle? Well, the tangent of this angle is opposite over adjacent. We notice that my opposite is B and my adjacent is A. So the tangent of theta 2 is B over A. And I can use this expression to actually define my reference angle, because now my reference angle, or theta 2, that's equivalent to the inverse of tangent of B over A. And these are three big ideas or three big components that we really have to remember when we try to represent complex numbers using trigonometric form. The real part is given to you by r cosine. The imaginary part is given to you by r sine. And now the reference angle is given to you by the inverse of tangent of B over A. Very important. So make sure that you do have this down. So now out of, I guess just for vocabulary here, now r, which again, r can also be seen as the distance from the point to the origin. So this r that we use in here, this distance from the point to the origin, which is exactly what we were defining right here from the beginning of the problem. So r is nothing more than the absolute value of the location given by the point to the origin. And we define that as being the modulus of z. And the data that we're using is what we call the argument of z. Okay, which in this case, we represented our argument by using theta subscript 2, because this is the argument. No, I'm sorry, it's just regular theta. Not theta 2. This is just regular theta for this example. Okay. Now, let's do some examples. So let's try to put everything together into a good example. So let me just make some space for myself here. So let's write down the complex number z in trigonometric form. Okay, so how do we go about this? Well, notice that in here, that's my real part, and that's my imaginary part. So this will be represented by my a, and this is my b, just negative 2 square root of 3. So how can we use, or how can we represent this number using trigonometric form? Well, the first thing that we have to do is to define the value of r, or the distance from the point to the origin, which we define as the modulus. So if that's the distance, then r is nothing more than the absolute value of the real square plus the imaginary square. Let's just plug that in here and let's see what we end up with. So the real is negative 2, and the imaginary is negative 2 square root of 3. So this is how we define the modulus, or at least the value of r. And if we compute this, we're going to end up with, so the first one is 4, and the second one is going to be 4 times 3. So now we got 4 plus 12, which is just 16. And the square root of 16 is just 4. So let's actually give a visual representation, because that's actually our hint. Our hint is to draw a diagram. So let's actually understand what exactly are we doing here. Well, I'm going to draw my diagram here on the bottom. Okay, so this is my diagram. Where exactly is this point that we're trying to graph? Well, I'm saying that my real part, let me use a different color here. I'm saying that my real part is of negative 2, so that's about negative 2 here. And my imaginary part is of a value of negative 2 square root of 3, which negative 2 square root times the square root of 3, it's about negative 3.4. So if we plot this in here, we're going to get when my x is negative 2 and when my y is negative square root of 3. So this is where my z point will be located at. So now let's actually start thinking about this problem very at least a little more deeper, because this is the reference angle, or at least this is the triangle that we'll be using. This is going to be a right triangle whose length here is of 2, but in the negative direction, and whose y component is going to be negative 2 square root of 3. And now this, if we take a look at the location of this triangle, this location is located on the third quadrant. And all we have done so far is say, look, if I measure the distance from this point to the origin, that's about 4 units. That's what we have just done so far. But what else do we need in order for us to define the complex number? Well, to define the complex number, I know the value of r, which we already found it here. And I also know I need to know my reference angle, or at least we're going to use this angle to define the argument of z. So let's think about this for a second now. So how can we define the measurement of this angle? Well, we do have a formula that we just discovered a couple minutes ago. I know that that reference angle is equivalent to the inverse of tangent of b over a. So I know that this inverse of tangent, so theta 2, is going to be given to me as the inverse of tangent of b over a, where in this case, b is negative 2 square root of 3, and a is negative 2, which, if we simplify this a little further, we have that this is just the square root of 3. And if we use our graphing calculator, you will see that tangent of inverse of square root of 3, that's nothing more than pi over 3. But let's see, why is it pi over 3? Well, it is pi over 3 because if we take a look at our unit circle, tangent is being defined as sine over cosine. So if we do square root of 3 over 2 divided by 1/2, you will get an output of square root of 3, which is exactly what we wanted to look at. So I know that the tangent of pi over 3 is equivalent to square root of 3. So now, but we have to be careful with how we're going to define this, because even though this is my reference angle in my circle, in my triangle, all this is saying is that this little angle that we do have here, this is equivalent to pi over 3. But we're not going to use pi over 3 when we're trying to use, or when we're trying to rewrite our number in complex form. What we want to use is the actual argument, and the actual argument is the total distance, or the total angular distance, from the first point up to where my line is being defined by r. So this is the argument. This is what we want to use. But because it is on the third quadrant, I know that this little distance right here, it's pi over 3. So therefore, my argument is going to be a whole pi plus pi over 3. And that will be equivalent to just 4 pi over 3. And this is something that is very important, and I want to put a lot of emphasis on. When we are defining complex numbers using trigonometric form, we're not just going to get the value that we get when we look at our unit circle. So I understand that the inverse of tangent of square root of 3, it is pi over 3, and that's fine. That only indicates this little distance right here. But the actual angle, or the actual argument that we're going to be using to define this complex number, is the total angular distance from the initial x-axis, or the real axis, all the way down to where r is being defined. So I know that this is pi, and I know that this is pi over 3, so therefore the total distance is the addition of them two, which is equivalent to 4 pi over 3. So now we have everything that we need to, because now I know that any complex number is being defined as r times the cosine of the argument plus the sine of the argument I. I'm just gonna keep the same format. I always put the I in the front. So now let's just put it all together. So now the complex representation using trigonometric form is just going to be r, which again, r, we found it to be 4. So now this is equivalent to 4 times the cosine. Again, it's not the cosine of pi over 3. It is the cosine of the total distance, which that is equivalent to 4 pi over 3. Plus I sine of 4 pi over 3. So now this is the right way to represent the complex number negative 2 square root of 3I using trigonometric form. And again, it's very important for you to understand this. It's not that we're just using the outcome of the inverse of tangent. The inverse of tangent is just going to give you the distance of my triangle, or the distance of this angular distance inside this triangle. But again, the real angle that we're using to define the complex number, it is the total distance that is traveled, the total angular distance, which is just, in this case, is going to be pi plus pi over 3. I hope that this was helpful. And this concludes our lesson for trigonometric form of complex numbers.